There are three types of control. First, we have the temporal control. This is a control based in time. Second, we have the state control. This is a control based in state level. And lastly, we have the hybrid control. This is the control type in which the two other control types are combined. So we have both temporal and state control. The purpose of programmable logic controllers, or PLCs, these are initially designed to replace relay logic boards for sequence device actuation and coordinate activities. It accepts input from a series of switches, and its output are sent to devices or relays. There are four functions of controller. First, the on-off control. Second, the sequential control. Third is the feedback control. And lastly, we have the motion control. There are also different control devices. First, we have mechanical control. Second, pneumatic control. Third, electromechanical control. Fourth, electronics control. And lastly, we have computer control. Programmable logic controller was originally invented in 1968, and its main function is a substitute for hardwired relay panels. According to National Electrical Manufacturing Association, or NEMA, PLCs are a digitally operating electronic apparatus which uses a programmable memory for the storage of instructions by implementing specific functions such as logic sequencing, timing, counting, and arithmetic to control through digital or analog input and output modules, various types of machines, or processes. The digital computer, which is used to perform the functions of a programmable controller, is considered to be within this scope. Excluded are drum and other similar mechanical sequencing controllers. Now this is a simple block diagram of PLCs. Actually, you don't have to memorize this right now. You'll understand more about this as we go along. So first, we need to understand what devices does a PLC actually interact with. First, we have input relays. These are connected to the outside world. They physically exist and receive signals from switches, sensors, and any other objects like this. Typically, they are not relays, but rather they are transistors. And then we have internal utility relays. These do not receive signals from the outside world, nor do they physically exist. They are simulated relays and are what enables a PLC to eliminate external relays. There are also some special relays that are dedicated to performing only one task. Some are always on, while others are always off. Some are on only once during power on and are typically used for initializing data that was stored. Third, we have counters. These, again, do not physically exist. They are simulated counters, and they can be programmed to count pulses. Typically, these counters can count up, down, or both up and down. Since they are simulated, they are limited in their counting speed. Some manufacturers also include high-speed counters that are hardware-based. We can think of these as physically existing. Most times, these counters can count up, down, or both up and down. Fourth, we have timers. Again, these also do not physically exist. They come in many varieties and increments. The most common type is an on-delay type. Others include off-delay and both retentive and non-retentive types. Increments may vary from 1 millisecond through 1 second. We can take a look at this later. Next, we have output relays. These are connected to the outside world. They physically exist and send on-off signals to solenoids, lights, and other output devices. They can be transistors, relays, or triacs, depending upon the model chosen. And then we have data storage. Typically, there are registers assigned to simply store data. They are usually used as temporary storage for math or data manipulation. They can also typically be used to store data when power is removed from the PLC. Upon power up, they will still have the same contents as before power was removed. Very convenient and also necessary, since power interruption can happen unexpectedly. These are a few examples of switches that are commonly used. The first one, we have non-locking switch. So in this one, if you press the switch, it will close the circuit, and then when you release the switch, it will open the circuit automatically. What's underneath is like a spring, so the switch bounces back to its open state. Next, we have the locking switch. This is the opposite of the non-locking switch. If you press the switch, the circuit will close and it will remain closed until you open it. And then we have a normally open switch. This one is denoted by a push button. So it's a push button normally open switch, meaning that the circuit is normally open if the switch is not pressed. And then we have the normally closed switch, meaning this switch is already closed, so the circuit is already closed, and it will open if you switch it. Next, we have single pole double throw switch. In this case, the switch has two ways in which it can let the current into. We have P1 and P2, so it is said to be double throw. Don't worry, this term, single pole double throw, the pole and throw, we'll discuss a little more about this later on. And then the break before make, so the circuit will open before the switch touches the other part of the circuit. And make before break, it is the opposite. The switch will touch the other part of the circuit before it breaks contact with the first one. So for the terms, throw is the number of states, pole is the number of connecting moving parts, or the number of individual circuits. So as you can see, single pole, double throw. So there's only one moving part, so single pole, one pole, and then two parts of the circuits in which the switch can make contact. So it has a double throw. And on the other one, we have double pole, single throw, double pole because there are two moving parts, and single throw because actually if you switch the state of the switch, it can either be open or closed circuit. And then here are the type of switches. We have the basic switch operated by a mechanical level. This is sometimes called toggle switch. And then we have the push button switch. An example of the switch is the button on your remote. Then we have a slide switch. This can be turned on or off by sliding. And then thumb wheel switch. And then we have limit switches, proximity switch, and photoelectric switch. Now, choosing a switch you will take a look at its specification, and the most common specifications you need to look at is its voltage and current rating. So you have to make sure your switches can handle the voltage and current on your circuit. Next we have relays. Relays. This is a switch whose operation is activated by an electromagnet called a relay. So you don't actually need to touch the switch in order to turn it on and off. You just need to add power or electrical current to the coil underneath that switch. So if a current flows through the coil, it will generate a magnetic field which will attract the contact of the switch. So the circuit will close. And you can also turn the current on the other direction to repel the switch. Now another component of a PLC is counter. Digital counters output in the form of a relay contact when a pre-assigned count value is reached. Okay, you'll understand more about this in examples. And then we have a timer component. A timer consists of an internal clock, a count value register, and an accumulator. It is used for or some timing purpose. So there. Again, you'll have a deeper understanding about this when you see an example. Then this is a basic example of a relay logic. Let's read through the situation. For process control, it is desired to have the process start by turning on a motor. 5 seconds after a part touches a limit switch, the process is terminated automatically when the finished part touches a second's limit switch. An emergency switch will stop the process anytime when it is pushed. So basically, this is a ladder diagram, also called contact symbology. It is a means of graphically representing the logic required in a relay logic system. So as I've mentioned before, this is a way for programming PLCs. So let's label the parts. The long vertical lines on the leftmost side and rightmost side are called rails. So we have 2 rails, and then each horizontal lines are called rung. These lines go from the left rail to the right rail. And then in these rungs, we can insert circuit components. In this case, there's a push button 1. This is the start, push button 1. So if you look at the circuit, once you turn push button 1 on, the circuit will close, so there will be current from the leftmost rung to the rightmost rung. And then there's another push button, PB2. This is for emergency stop. So visually inspecting, if we push this button, the circuit will open and there will be no current flow. And then we have R1, this symbol, circle. This is usually the output. So in this case, it may be a motor. So once we turn this on, R1 turns on. And so the R1 that is in parallel with RB1, denoted by 2 short vertical lines, two short vertical lines. So it will also turn on bypassing the PB1 switch. So even if the PB1 switch is switched off, the circuit will open. There will still be current flow from the left rung to the right, from the left rail to the right rail via this R1. And then on the lower rung, we also have R1. So when R1 is turned on, the A output will also turn on. And then if we want to turn this off, we can just switch PB2, the emergency stop button, switch it to switch the entire system off. This is another example of ladder representation. So on the left side, as you can see, the inputs, the two vertical lines, we have switch 1 and switch 2. The output is a coil, and the end, we have the end rung. It's just there to note that it is the end of the program. And then on the right side, again, we have our inputs. This time, the inputs has a dedicated identification name. So the switch 1, we have 0000. This depends upon the port of the PLC device that you will use. So switch 1 is connected to port 0000. Next, we have switch 2. Switch 2 is located in port 0001, and this switch is normally closed. Switch 1 is normally open, switch 2 is normally closed, denoted by the diagonal line between the two vertical lines. And then finally we have the coil. It is located in port 0500. It is an output. And then of course we have the end. And then the scan cycle. A PLC resolves the logic of a ladder diagram or program rung by rung from the top to the bottom. Usually all the outputs are updated based on the status of the internal registers. Then, the input states are checked and the corresponding input registers are updated. Only after the inputs and outputs have been resolved is the program then executed. This process is run in an endless cycle. The time it takes to finish one cycle is called the scan time. So as you can see, we have in the circle, there's a beginning, which will then proceed to the output and then input and then resolve logic, and we have an idle state, and then it will return again to output and then input and then resolve logic and then an idle state again. So the entire time, the actual time for this will depend upon the length of the program and the complexity of the program. So we have a list of PLC instructions in this slide. These are the components that we put in the PLC ladder. So we have relay, timer and counter, program control, arithmetic, operations, data manipulation, data transfer, and others, which are specialized functions such as sequencers. And then for the logic states, for example, the switches can either be on or off. Other words for on can be true, contact closure, energize, close, etc. Off, also known as false, contact open, de-energize, or simply open. Now do not confuse the internal relay and program with the external switch and relays. Internal symbols are used for programming. External devices provide actual interface. Now in the notes, we use the symbol, this tilde, to represent negation, or sometimes called not, negation or not, or that tilde symbol, and or are logic operators. So we have the negation, the not, and then the and then the or. Those are our logic operators. Now for the AND logic, in the first image, we can see PB1 and PB2 are connected in series with R1. So in order to turn R1 on, we have to turn on both PB1 and PB2. As compared to the OR, the second image, PB1 and PB2 are connected in parallel. So turning on either PB1 or PB2 will turn the coil R1 on. So you see the difference between AND and OR. For AND, both must be on, and for OR, just one would suffice. And then another case for AND, as you can see in the second rung, we have two switches, PB3 and PB4, but PB4 is a normally closed contact. PB3 is normally open. We just need to switch PB3 on in order to turn on R2, the coil R2. So in this case, this is still an AND logic. So here we can see a combined AND and OR. So we have PB1 in parallel with PB2 and PB3. So PB2 and PB3 are connected in series. Now in order to turn R1 on, we can either turn PB1 on or turn both PB2 and PB3 on. Of course, we can also turn all three switches at the same time. That would also turn R1 on. And now if we write this down, as you can see, R1 is equal to PB1, or we have this parenthesis, PB2 and PB3. Take note, the parenthesis is important in this case. This is just like mathematical operations. And then for the relays, a relay consists of two parts, the coil and the contacts. So the contacts are what we have used as inputs. So it can be expressed as two vertical lines for normally open, two vertical lines with slash in the middle as normally closed, and then we have an arrow up for off-on transitional and arrow down for on-off transitional. Now, we barely use the on-off and on-off transitionals. Most of the time, we use normally open and normally closed contacts or switches. And then for the coil, these are sometimes what we use for outputs. So we can see energized coil, de-energized coil, a latch and unlatch. Now, energized coil are what is mostly used. De-energized latch and unlatch are used for special occasions. Then we have timers and counters. For timers, we have retentive on delay, retentive off delay, and reset. And then for counter, we have counter up, counter down, and counter reset. Now these are pretty self-explanatory based on their names, but we'll take a closer look at these timers and counters in the examples to follow. So for the sequencers, sequencers are used with machines or processes involving repeating operating cycles, which can be segmented into steps. So in this case, as we can see, we have 4 steps, 1, 2, 3, 4. We have 3 outputs, A, B, and C, and we have dwell time. The dwell time is the amount of time in which we will dwell in this step. So for step 1, A is on, B is off, C is off, and it will last for 5 seconds. Step 2, A is on, B is on, C is off, and it will last twice as long as the first step, so it will last 10 seconds. Step 3, off, off, on, it will last only 3 seconds. And lastly, for step 4, we have output A is off, output B is on, and output C is off, and it will last for 9 seconds. So this is the basic operation of sequencers. And let's take a look at a real-world example. programming a PLC. Let's take a look at the situation. Oil is consumed randomly. The tank needs to be refilled by turning on a pump. Two hydrostatic switches are used to detect a high and low level for the oil. So as you can see, we have PLC connected to two hydrostatic switches, which are placed at different levels in the tank of oil. So we have a long hydrostatic switch, which will detect the low level, and a higher hydrostatic switch or shorter hydrostatic switch that is placed on a higher level that will detect if the oil is in a higher level. So these will serve as the input for our PLCs. And of course, the output of the PLC, it must be the refilling of this tank. So this is the ladder logic for the tank. Again, these numbers 0000001, these are for identifications of the switches or the inputs, and then we have the 100 for the coil, and then 0500 for our output, and then of course in the last ladder we have end. So these are the steps in which the logic for each relay and coil will go through in the system. So basically, if both switches do not detect oil, both switches will remain in the on state or true state, and if they detect oil, they will switch to a false or off state. So let's take a look at a simulation for this. So how does it work? So there, did you see that? All are true, one is false. Then the oil starts filling up, both are false. The tank will start to drain. Both switches are true. And then false, drain. Okay. It may be too fast, but you can actually restart this part of the video so you can watch it over and over if you need to understand more of it, or you can go back to the previous slide to see the step-by-step transition of the system.